In Chapter 5 of the Methods text and Chapter 6 of the notes, we're going to cover two important topics: curve fitting and interpolation. Curve fitting is used when we have many data points that we want to fit to a function. The function may be any general function of the data. It could be a line, it could be a polynomial, it could be a transcendental function, or some combination of these. This is often used to select model parameters that minimize the error between each data point and the model. And it can be used for model discrimination when combined with measures of the goodness of fit. Interpolation is used to find a function that exactly matches a set of data. The interpolating function can then be used to estimate values of intermediate points. Interpolated functions will also be used later in the semester to find derivatives and integrals of data. Curve fitting is accomplished using regression methods. A model regression method determines the unknown coefficients of a model equation. We'll talk in this module about linear least squares regression, nonlinear least squares regression, and multiple linear regression. These can all be used to extract model parameters from data, and the type of regression that you select will depend on the form of the model. We'll also talk about measures of the goodness of fit. These can be used to discriminate between models, to answer the question which model is a better representation of the data. We'll introduce the coefficient of determination, which is called r squared, the adjusted r squared, or r bar squared, and the standard error of regression as three different measures of the goodness of fit. And we'll talk about when to use each of these. Here are two examples of using curve fitting to extract important information from experimental data. Both of these come from research in my research laboratory. In the example on the left, we're looking at data showing the mechanical relaxation of the stress in an agarose hydrogel that's under compressive strain. The data are fit to a model that contains three exponential decays. Each exponential decay has two parameters, a capital E sub I and a time constant tau sub I. By using least squares regression, we can select the values of E sub 0 and E sub I and tau sub I that make the model best match the data. In the example on the right, experimental data from a technique called X-ray photoelectron spectroscopy is shown in the open circles. You can see that this data has a significant amount of noise. Each of these data sets is fit to the sum of multiple peaks described by a combination of Gaussian and Lorentzian equations. Those peaks are shown in the broken lines. Each of these peaks has multiple parameters that describe it, including a position along the x-axis, labeled as binding energy here, a magnitude indicating the size of the peak, and a parameter describing the width of the peak. In this case, the data are fit to the sum of three different peaks, and each of those peaks has three parameters describing it. So a 9-parameter model is used to fit these data. The sum of the three peaks, each shown in the broken lines, is shown in the solid line that goes through the data points. By resolving the position, magnitude, and widths of these peaks, we can determine how much of the nitrogen in this sample is in ammonium groups, amide groups, and amine groups. In both of these examples, the curve fitting is used to obtain model parameters. In the next video, we'll introduce the technique of linear regression.